Hi, so in this video we're going to be doing an AP Physics 1 released FRQ from 2021. So for our question, we are going to solve 1, 2, 3, 4, and 5 like a full-length FRQ, which is an hour and 30 minutes. So let's start off with our first question. We have a stunt cyclist builds a ramp that will allow the cyclist to coast down the ramp and jump over several parked cars as shown. To test the ramp, the cyclist starts from rest at the top of the ramp and then leaves the ramp and jumps over 6 cars and lands on a second ramp. So HO is going to be the vertical distance from the top of the first ramp and the launch point. So the top of our first ramp to our launch point is that H initial. Then our theta initial is the angle of the ramp at the launch point from the horizontal. We have X initial as the horizontal distance traveled while the cyclist and the bicycle are in the air, and M initial is the combined mass of the stunt cyclist and the bicycle. So what we're going to do is we want to derive an expression for X initial in terms of our physical constants. So our approach here is we are going to use energy conservation. 2 points we can identify are when we're at the top and also when we're at the bottom. When you're up here, you're going to have kinetic energy as a part of your energy total. And when you're at a point where you're low, you're going to have UG here. You're going to have kinetic energy at the bottom because you have a higher height, MGH. So your height is going to be scaling with your potential energy. And then down here, you're going to have a maximum speed. Now, what we can do here is we can set, since the cyclist is going to start from rest at the top of the ramp, when we write our equation, we can write K initial is equal to 0. That means that we're going to use our launch point as our 0 level for our gravitational potential energy as well, because we can choose whatever point is going to be the most convenient for us. So then at the top of the ramp, we're going to say that this is going to be M initial, G, H initial. Then at our launch point, we're going to say from here where we start our projectile motion, we're going to say our potential energy F is equal to 0 because this is going to be our new X is equal to 0 over here. Convenient for us when we're doing our conservation of energy. Then we can say that our KF is going to be equal to 1/2 here at this point. M initial, V initial squared. So now let's write our energy conservation over here. If we have our conservation of mechanical energy, so K initial was equal to 0 because the cycle started from rest. Now you're going to set M initial, G, H initial equal to 1/2 M initial, V initial squared. So you can cancel out your M initial from both sides. You have G, H initial is equal to 1/2 V initial squared. After this, you can multiply both sides by 2. You get 2GH initial is equal to V initial squared. You take the square root of both sides. You get V initial is equal to the root of 2GH initial. Now you have to break your launch velocity into components because whenever you have a vector, you have movement in the upward direction and also in the rightward direction in this case. So we'll define that as our positive X direction and this is our positive Y direction. The horizontal component is equal to V initial cosine of theta and the vertical component is equal to V initial Y, V initial sine theta. Now we had to find, so we've already broken it up into components. Let's find our time in air. So because we know we have a horizontal launch where we start at our launch and we end at our launch at the same height, we are going to say that for projectile motion, we have our T is equal to 2V initial Y component over G. So now we know that V initial Y was that V initial sine theta, so we can write this as 2 V initial sine theta initial over G. So now to find our horizontal range, you're going to have X initial, your distance that we traveled, is equal to V initial, X component, times T. Well, conveniently for us, we already solved for both of these, V initial cosine theta initial, and also 2V initial sine theta initial over G. This will be equal to 2v initial squared sine theta initial cosine theta divided by g. So you can use that 2 sine theta cosine theta initial is equal to sine 2 theta initial. This is your double angle identity in trig. So if we use that, we can look inside of our equation here. We have exactly this inside of our numerator. Therefore, we could rewrite this by using that same expression. We have 2gh initial times sine 2 angle initial divided by g. And we can cancel out that g right here now. So x initial is just equal to 2h initial sine 2 theta initial. And that is your answer for part A. Now, we're asked if the vertical distance between the top of the first ramp and the launch point were 2h initial instead of h initial with no other changes to the first ramp. What is the maximum number of cars that the stunt cyclist could jump over? So, what we're changing is, instead of h initial, we have 2h initial for our first ramp. Our first ramp is going to be here. So we're asking if we are going to double it to 2h initial. So now we know from part A, we have our expression over here for x initial. We can actually use this. So with this, we have 2h initial here, 2 theta initial. So if we have h initial become 2h initial, we have an x nu equal to 2 times 2h initial sine 2 theta initial for h initial sine theta initial, and that's x nu. So our original one was here. Our new one is here. So that means that we can see that if we took the ratio of those, that would be for h initial sine theta. So then this is equal to 2, a ratio of 2 to 1. Therefore, x nu is equal to 2 times of x initial. So we know that originally we have a jump that clears 6 cars. And that's a distance. This is our distance of 6 cars. Therefore, if we have twice of that for x initial is equal to that of a nu, that means that in our new jump, this jump would clear 12 cars. Because we can see our range x is directly proportional to h initial. So if you double h initial, it's going to double the distance jumps. Now, let's move on to our next part. Now, on the axes, sketch a graph of the vertical component of the stunt cyclist's velocity as a function of time immediately after the cyclist leaves the ramp to immediately before the cyclist lands on the second ramp. On the vertical axes, clearly indicate the final and initial vertical velocity components in terms of physical constants. We're going to take the positive direction to be upwards. So we already have from over here this formula for v initial. We can use this. We know that our initial vertical component is v initial sine theta. So vy initial is equal to this. So that means that if we were to find our vertical velocity, we know that the cyclist is going to land at the same height as launch, as we can see here. And we can see we're going to have no air resistance. So that means that our vertical component is going to have the same magnitude but opposite sign. Now, that is going to be VYF is equal to negative root 2 GH initial sine theta initial. Now, we know for our acceleration, AY is going to equal to negative G anywhere on Earth. Therefore, that means that Vy decreases linearly with time. As a reminder, is equal to delta V over T. Therefore, if you have it always equal to negative 9.8, you keep dividing it by numbers like 5, or let's start off with 1, and then negative 9.8 over 2, negative 9.8 over 3. It's linearly going to decrease as our x values get bigger. Therefore, what we can do is we can graph a straight line with a slope of negative g. So our m slope will equal to negative g, starting at positive 2hg sine theta, root 2gh initial sine theta, and it's going to end at negative h initial sine theta. So that is our m slope. Now let's move on to our next question. A group of students is investigating how the thickness of a plastic rod affects the maximum force F max with which the rod can be pulled without breaking. Two students are discussing models to represent how F max depends on rod thickness. Student A claims that F max is proportional to the radius of the rod. Student B claims that F max is directly proportional to the cross-sectional area of the rod, which is the area of the base on the cylinder, shaded gray in the figure above. These students have a collection of many rods of the same material. The rods are all the same length, but come in a range of different thicknesses. Design an experimental procedure to determine which student's model, if either, correctly represents how F max depends on the rod's thickness. So, to summarize, student A is going to be F max is proportional to R. Student B is F max proportional to cross area sectional, and that is going to be equal to pi r squared because we have a circle, right? So that means that F max would be directly proportional to r squared if we're just looking at two things inside of our relationship, and we just get that relationship we can focus on. So let's think about things we would have to measure. If we were measuring, we would need to find the rod diameter, which we can call D. We would use a caliper or a ruler to measure that distance, length. Now, you would also have to find the rod radius, which you could get from just dividing diameter over 2. So we'll say this is calculated from diameter. We also need to get the maximum force before breaking. This is called F max. We could use a force probe or a spring scale to measure this. Now, let's design an overall procedure with our variables here. So we have a spring setup. If you've done a lab in AP Physics, then this is just going to be remembering what you did from the lab, essentially. Now, let's just write some steps out. You're going to want to sort the rods by thickness. Since all the rods are the same material and length, the only intended changing variable is rod radius 2, or radius R. For each rod, measure diameter D with a caliper. And then you need to calculate your radius. R is equal to D over 2. We're gonna clamp one end of the rod securely, attach the other end to a spring probe or a spring scale so we can measure that. Next, you're gonna pull straight along the length of the rod, gradually increasing the force until the rod breaks. Next, you're gonna record the greatest force reading just before the rod breaks. This is equal to your F max. Now, we're going to repeat this for several rods of the same R and average the values of F max for that radius. Now, we can specify that we're going to repeat the process for all 6 thicknesses. We want multiple data points. You're going to graph F max versus R. Now, we're going to think, how can we test student A and student B based off what we know? Well, if we're maxing F max versus R for student A, that means that if the student is right or wrong, we can know that whether the graph is a straight line through the origin and for student B, what you can do is you can check, is the graph quadratic in R, or you could make a graph for F is max versus R squared and check if it's linear through the origin. Now, let's graph for the 2 models. So here we are already given some of our experimental data based off the experiment. So we have the point R initial, F initial given. And what we are going to have, also we need to talk about experimental uncertainty first. So for uncertainty, what we can do is measure each rod's diameter carefully. You could also do this more than once and average the measurements. Another thing you could do is you could test multiple rods of the same radius and average the measured F max. You could pull slowly and also straight, so F is applied consistently. And you could also calibrate your force probe or scale before you use it. And keep environment constant. Now, for graph A, we can expect this to be our delta y for our graph A. We're going to have student A, which is going to be delta y over delta x, and that's F initial over R initial. For our graph B, this is going to be delta y over delta x again, and this would be F initial over R initial squared. This should be, according to students' predictions, a straight line, and then this is going to be our slope, right? And then here, this should be a concave up quadratic. So both of our graphs must pass through R initial, F initial. So since we are going to have, for student A, we say that F max proportional to R, therefore F max will be equal to KR. Now we can use our point R initial, F initial, and then you're going to get F initial is equal to KR initial. Then you solve for K, that's going to be F initial over R initial. So for graph A, you're going to have F max is equal to the equation F initial over R initial times R. And let's indicate all this work is for graph A. Now for graph B, we are going to have concave up and quadratic as what it should be according to the student. Well, we know that F max will be proportional to the area, which is equal to pi r squared. We know pi is going to be constant, therefore we could write this. F max is equal to c r squared. We'll say that c is equal to constant. Therefore, F initial, if we sub in this point, for R initial, F initial, we're going to have F initial is equal to CR initial squared. C is equal to F initial over R initial squared. Therefore, F max is equal to F initial over R initial squared, R squared. And this is concave up through the origin and passes through R initial, F initial. Now, what are some points that would be on both of these graphs? To help us graph these, we would have 0, 0. Here we would have 0, 0. What about over here? Some points we could graph here. This is square, so we have square numbers. So since the graph only goes up to 10, let's start off with labeling our axes. So you want to have clean, even units for your axes, typically. So we'll number this up to 10. We'll call this 10F initial, and halfway we can have this as 5F initial. This graph is actually not perfectly on it, so we can have 8F initial here. Then we have our 6F initial, 4F initial, and then 2F initial. And then here we're gonna have 1R initial, 2R initial, 3R initial, 4R initial, 5R initial. And we can graph these. So our intersection point is going to be around here. So we're gonna have let's draw B afterwards, but this is gonna be at around 5 for our line A. And then for B, we are gonna have this quadratic curve with just the first or the second half of the quadratic, and it's gonna be around 3. And we have an intersection point over here. Now, for our next part, what we want to do is we're asked which student's model is more closely represented by the evidence shown in the graph you drew in part C. Well, we're gonna see that student B's is more closely represented because student B, they said that we had F max that was proportional to R squared, but in part C, we are not going to have a straight line. No straight line. We have that curve upward because F max does not decrease linearly. You can see this when we look at our data again, because we have these values that are going to be equal length intervals, and they're all going to be increasing by relatively small values, different radius, and we can see that the F maxes, they're just going to be very large. On to question number 3, we have a student of mass MS is standing on a smooth surface and uses a stick to push a disc of diameter MD. The student exerts a constant horizontal force of magnitude FH over time interval from t is equal to 0 to t is equal to tf while pushing the disc. Assume that there is a negligible friction between the disc and the surface. So, assuming that our disc is going to start at rest, we want to find an expression for the final speed Vd of the disc relative to the surface. And we're going to use our physical constants. So if we think about our disc, right, and our whole entire system, we have our person, and they have their stick, and then we have our puck right here. Now, we can think that if we're looking for the final speed, we're going to have to get a kinematics involved in here, not projectile but kinematics. So we have our summation of x forces because we have our horizontal forces mentioned here. So in our horizontal direction, we're going to have the mass of the disc and acceleration of the disc. So the force of the hockey stick is equal to md and the acceleration of the disc that it's going to be undergoing. Now, that's just your F is equal to ma, by the way. That's just Newton's second law. And we have our AT is equal to our F of our hockey stick over the mass of the disc. Now, because we have constant acceleration, right? Because the disc is going to be constantly accelerating, a horizontal force of FH, as we're stated right here. That means we can use kinematics, which requires a constant acceleration. So we know that the disk is going to begin at rest. So that's equal to Vd initial is equal to 0. So we know that the force is going to be applied over an interval for a time of tf, right? So then the disk is going to accelerate for a time tf. We'll use this kinematics equation. And we can just substitute in. And we get FH is TF over md as our expression. For our second part, we have assumed there's a negligible friction between the student's shoes and the surface. At time tf, the student slides with a speed vs. Derive an expression for the ratio of the velocity of the disc over the velocity of the student. So we have to think about our entire system that we have. It's going to be the student and the disc. So we know that initially that VD initial is equal to 0 and V student initial is equal to 0 because they are going to both start from rest. We know our momentum equation on your sheet is equal to P is equal to MV, right? So if you have your V initial is equal to 0, that means that your initial momentum in total is going to be equal to 0 because of multiplying both our masses by 0. And because we have negligible friction with the ground, that means that there is no net external horizontal forces on the student disc system. So our force, the force that we are going to have on the disc, so and the disc force on student, this is going to be an internal Newton's third law pair. When you have this, you're going to have that horizontal momentum is going to be conserved. Because all of the momentum just stays in it. And we have, for every action, there's an equal and opposite. So your final momentum is equal to your initial, and that's equal to 0. So now let's write out our final momentum. So that will be mass of the disc, velocity of the disc, mass of the student, negative Vs equals to 0. Now, MD, VD minus MS, Vs will equal to 0. We want to find the ratio MD, VD, MS, Vs. We want to find the ratio from this. So we can divide both sides by MdVs, here again, MdVs. We get that VD over Vs is MS over MD. Or VD over Vs is equal to MS over MD. So this makes sense because we know that your system is starting with 0 momentum, right? So then after the push, the student and the disc exert, they're going to have equal and opposite momentum. And since we know that momentum is mass times velocity, the ratio of the speeds is going to be the inverse of the masses. Inverse ratio of the masses. Now, assume the student's mass is greater than that of the disc. Mass of students greater than the disc. Sketch the graphs for the student and the disc as functions of time, between time is equal to 0 and time is equal to 2 time final. Assume that neither the disc nor the student collides with anything after the time is equal to time final. On the vertical axis, label VD and VS. Label the graphs S and D for the student and disc, respectively. So here, what we're going to do is, first, we're going to require a straight line segment between 0, T, and TF. We know they're both going to start at the origin because we start from rest. They're going to have different positive slopes because they're just going to be having that change in X differently because V delta X over T. We have VD is greater than VS, right? So what about our disc speed during our push, which was 0 less than T less than or equal to TF? So we had from part A that AD was equal to FH over md. So then v dt, that function is equal to vh over mg times time. Now, when you are at your t is equal to tf, you have vd is equal to fh tf over md. What about for our student during our push of 0 less than or equal to t less than or equal to tf? So because we have Newton's third law, right, if the student pushes the disk forward with a force of fh, the disk is going to push the student backward with this force of fh. So then when we are looking at on the student, you're going to have the summation of fx is equal to ms as. So if you take the magnitude, VH is equal to ms as, and as is equal to the ratio of fh over ms. So then the student speed is going to be vs t. We have our fh over ms times t. Then at where value t is equal to tf, vs will be equal to this. Since we know that we have to compare, we know ms was greater than md. So fh over md is greater than fh over ms. So then our disk graph is going to have the larger slope. We also know that vd is vh tf over md, and this is equal to vs. Therefore, the speed disk is always going to be greater than the speed of the student for time is greater than 0. Now, what about our behavior after TF? Well, when we're at T is equal to TF, we have that the force is no longer applied. And there is no negligible friction. So each object has 0 net horizontal force. Newton's first law is an object in motion stays in motion until something obstructs it, right? So each object is going to continue at a constant speed. So for our TF is less than or equal to T, is less than or equal to 2TF, VD of T is equal to FH over TF over MD, right? And then FS T is equal to FH TF over MS. These are both going to be horizontal lines, and let's write these lines on our graph here. So we know that both of the graphs, they are going to be starting at 0, 0, right? Because they started from there. Now, what happens after this is that they are going to increase. So they're going to increase until TF linearly, and then they're going to be that level part, right? So that's D. And then for this one, we're going to go here, and then this goes, that's for the student. And we'll label this the speed of the student, and here the speed of the disk. Now, for our next part, we have that the disk is now moving at a constant speed v1 on the surface toward a block of mass mb, which is at rest on the surface shown above. The disk and the student and the block collide head-on and stick together, so we have a perfectly inelastic collision. And the center of mass is going to be moving with v center of mass. Suppose the mass of the disk is much greater than the mass of the block. Estimate the velocity of the center of mass of the disk block system. Explain how we got this. Okay, so here what we're going to do is we have that v center of mass is approximately going to be v1. So if we know that the disk is much more massive than the block, right? that means that the block is going to have a very little effective motion on the system. So that means that the center of mass is going to be closer to the disk. And therefore, it's going to move about the disk speed for the center of mass of our system, of our new combined object. So that's why we get V center of mass is going to be approximately V1, because we have one object that's going to overtake. It's much more massive. So the center of mass is always going to lie near the object that's just a larger mass, right? Now for part 2, we have that suppose the mass of the disk is much less than the mass of the block. Estimate the velocity of the center of mass of the disk block system. Explain how you arrived at your prediction without deriving it mathematically. So here we can also add that for this first part, written explanation. So the block Now for this second question, we have that, or no, this is for here. Suppose the mass of the disk is much less than the mass of the block. Estimate the velocity of the center of mass of the disk block system. Explain how you arrived at your prediction without deriving it mathematically. So we're going to say that the mass of the block dominates the location of the center of mass, so it barely moves because the center of mass is going to dominate the entire system, because having a larger mass is going to influence how the mass is distributed. The mass is just distributed in that way. So the center of mass wants to be closer to the center of where all of our total mass is, right? So now for part 3, now suppose that neither object's mass is greater than the mass of the other, but they are not necessarily equal. Derive an expression for V center of mass. And how would we do this? Well, we have to think about pre-collision before collision. Well, what we have is our disk is going to have a block of MD and has a speed of V1. And then we have a mass B. Your block is going to be at rest, right? So then we can write your initial is equal to your final, right? Because we have, for all collisions, you're going to have conservation of momentum. Therefore, we have for our P initial side, we are going to have MdV1 plus MB times 0. Now, this will be equal to MdV1, and that's equal. Now, our center of mass relationship, because we have a one mass that's just combined now, because the two masses are perfectly inelastically combined. So we have the center of mass here, and this is going to be equal to our expression. Now we just have to solve for our V center of mass, right? So then you have MdV1 over MD plus MB, and that's going to be your expression, right? Now consider the scenario from part C where the mass of the block was much greater than when the mass of the disk was much greater than the mass of the block. Does your equation from V center of mass agree with your reasoning from part C1? Yes. Well, that's because for us, we have that, our V center of mass we just found, right? What is this? MD V1 over MD plus MB, right? So then if we have that MD is going to be much, much greater than MB, that means that our denominator inside of our equation is going to become MD plus MB, and that is going to be approximately closer to the value of MD, because that's going to dominate. Like imagine you had like 2,500,000 and you had 1. Well, which one's going to be closer? It's going to be the big number. And that means that we can see that the V center of mass equation is approximately going to become MdV1 over MD, right? So then V center of mass would be approximately equal to V1, which matches the reasoning we had from part 1. And this is that limiting case that we have. So the disk's mass is much larger, and the small block's mass hardly changes the denominator, so the center of mass speed is going to approach the disk's initial speed. Question 4. A cylinder of mass m initial is placed at the top of an incline of length L initial and a height of h initial as shown above, and released from rest. The cylinder rolls without slipping down the incline and continues rolling across a horizontal surface. On the grid below, sketch a graph that represents the total kinetic energy of the cylinder as a function of the distance traveled by the cylinder as it rolls down the incline and continues to roll across the surface. So if it starts from rest, that means that your V initial is going to be equal to 0, and kinetic energy is 1/2 mv squared. So therefore, your kinetic energy would be 1/2 m times 0 value, making your kinetic energy in the initial part of your equation is equal to 0. Therefore, your K total will equal to 0 because we're going to have conservation of energy since there was no mention of friction here, so we can assume that. Therefore, when you are going to be at your distance traveled at x, it's going to equal to 0. Now, when you're thinking about rolling down an incline, right, that means that your gravitational potential energy is going to be converted into kinetic energy. So since we have an incline that is straight, that means that the vertical drop is going to be proportional to the distance that you traveled along the incline. Now, that means that we have a loss of gravitational potential energy, and that's going to it's going to increase linearly with our distance that we traveled. So the total kinetic energy is going to increase linearly. So we can think about it like this, right? So up here, again, that's your kinetic energy, and then down here, you're going to have your up here, you're going to have your UG, which is your potential energy. Down here, you're going to have your kinetic energy maximum because you're all the way down here. All that potential energy has been converted into speed. And, well, we have delta Y, right? So this will be equal to H initial over L initial over times X. So that is the X distance moved along incline. This is our cylinder movement. This is going to be our vertical drop. Well, we know that our decrease in gravitational potential energy, well, that's UG. That's just changing UG. We have M initial, G delta Y, and we have delta Y over there, right? So we can just plug that in here. We have H initial, L initial times X, which is this expression here. Now, what can we do next? Well, we know we have conservation of energy again because of our rolling without slipping. So our K total would equal to the same thing, M initial, G, H initial, L initial times X. For our time, or for our 0 is less than or equal to X, less than or equal to L initial. So that's for our distances. So that means that from there, from X is equal to 0 to L initial, we're going to have a graph with a straight line and a positive slope. Now, when we're at the bottom of the ramp, right, when we're at L initial, X is equal to L initial, that means that you have dropped the full height, right? Therefore, your K total max is M initial, GH initial. Well, so after that cylinder reaches the horizontal surface, that means that the height is no longer going to change. And since it continues rolling without slipping on this horizontal surface, right, its total kinetic energy is going to stay constant. And there's no further change in our gravitational potential energy over here. So that means the total kinetic energy is going to remain at that constant value. So from X is equal to L initial all the way to X is equal to 2 times of L initial, that is going to be that horizontal line, right, at K total. So it's going to be K total is M initial, GH initial, your horizontal line, because this would be a one value that should be a constant, right? And that's from X is equal to L initial to 2L initial. So for our graph, you're going to start at the origin, and you're going to draw a line up to with a positive slope. And then it's going to be horizontal here. Now, for our next part, well, let's explain this real quick. So the cylinder is going to lose gravitational potential energy at a constant rate per unit traveled, right? So that means kinetic energy is going to increase linearly as we continue. And then on the horizontal, because our height stays the same, the total kinetic energy stays constant. We have that the cylinder is again placed at the top of the incline. A block of mass m initial is placed at the top of a separate rough incline at a length L initial and height h initial as shown above. The cylinder and block are released at the same instant, and the cylinder begins to roll without slipping, while the block begins to accelerate uniformly. The cylinder and the block reach the bottoms of their respective inclines with the same translational speed. In terms of energy, explain why the two objects reach the bottom of their respective inclines with the same translational speed. Provide your answer in a clear, coherent paragraph. Okay, so basically, when you're at the top, right, we know that they're both going to start with the same UG, regardless of cylinder versus block. And we know that they are going to both have the same mass initial, so that means that the object Earth system, which is going to be our M initial, GH initial, right, that is going to start with the same gravitational potential energy for both objects, right? So then we know that the object is going to roll down its incline for the cylinder without slipping because it's a circle, right? And we know that that's going to convert that energy into kinetic energy. But we have to remember that kinetic energy is going to not just be translational, it's going to be split into rotational plus translational. So here, your E total is K rotational plus K translational. And also, some of that mechanical energy is going to be dissipated because you're going to have friction acting on the block as well. Now, with all those things, we need to think about how we can put all that together. So in this explanation, we have that both objects start with the same height h initial, right? Same mass m initial. So here, same mgh initial. So the cylinder rolls down its incline without slipping, and the initial gravitational potential energy is converted into kinetic energy. Kinetic energy is split into K trans and K rot. Now, the block is going to have gravitational potential energy transformed into translational energy only, right? But some of that mechanical energy we lose from the friction, and the cylinder and the block are going to reach the bottom with the same translational speed because they have the same translational speed there, 1/2 m initial v squared. So that means that the amount of energy that went into the cylinder's rotational kinetic energy must be equal to the amount of energy that is dissipated by the friction for the block. So you have friction in one scenario, and then the other one, we roll without slipping. And when you have rolling without slipping, things you have to remember is there's going to be no relative motion at the point of contact. That means that no energy is going to be lost. The kinetic friction. And also, your static friction is going to be necessary to provide the torque that prevents the slipping. That slipping usually happens when you have acceleration or braking or an incline like here. So when you're at each point of the ball, right, it's instantaneously at rest because the point of contact keeps changing, right? So remember that your static friction is going to be necessary, and we have no energy loss. So that means that when we see that some of the energy has been dissipated in friction for the block, here we have some of it goes into rotation. So we're going to say that what we're saying with this is that the amount that is in the translation and left over from not the friction that's going to be equal to how much is going to be left in the translational motion once you factor in the rotational motion for the cylinder. On to question 5, we have two pulleys with different radii are attached to each other so they rotate together about a horizontal axle through their common center. There is negligible friction in the axle. Object 1 is going to hang from a light string pulled by the larger pulley, while object 2 hangs from another light string wrapped around a smaller pulley, as shown on the figure above. So we have M initial, 1.5 M initial for object 2, R initial for smaller, and 2R initial for the larger pulley. Now, we want to find the magnitude of the net torque on the object's pulley system about the axle after the pulleys are released. So what we have here, we can first write how after release, we know that object 1 is going to accelerate downward, right? So this object is going to go down. We'll make that our positive direction, and that's our acceleration. So that means that the system is going to rotate by the direction caused by object 1, right? So system rotates in this direction, which is our counterclockwise direction. Counterclockwise is the positive direction, by the way. And we can start by finding the torque, right? So then we know that for object 1, it's going to be on the larger pulley, right? So we have that R1 is equal to 2R initial. So we know that the weight is FG1 is equal to M initial G, and then we can find the torque 1, which is equal to R times F sine of theta, right? So then we know that the lever arm R is going to be 2R initial. That's going to be the distance from which the force is going to be applied, right? And then we have the M initial G. And we have sine of 90. Sine of 90 is equal to 1, right? So that's just why we multiply by 1 here. We don't really have to write that, but yeah. And just looking here, just so that you remember, this is for object 1, right? So you can see that this angle here, this is 90 degrees, right? So that means you have a lever arm R. When R is equal to 0, you have no torque because it's directly acting at the center, so it doesn't do anything. The further you're away from the center, that means you're going to have a larger force that is produced. So you want to maximize R to maximize your torque, right? So here, that's your torque 1, right? So this will be equal to 2M initial, GR initial. Now we have to look at object 2, right? Object 2. So for object 2, we have this smaller pulley, and that is R2 is equal to R initial. So FG2 is equal to 1.5 of M initial G. So then the torque magnitude is equal to R initial 1.5 M initial G. And again, we have a sine 90, which is equal to 1, and this simplifies to 1.5 M initial GR initial. So that's torque 1 and torque 2. So now we had to find the direction of the torques, right? So we know that the torques are going to act in the opposite rotational directions. If you have torque from this object, it is going to make the object go from object 1, it's going this way in the counterclockwise direction. But this one is making the object go in a clockwise direction. So they're opposing each other. This is negative, this is positive. So then we can just set up our equation with the summation of torques. They're in opposite directions, so that means we are going to take the difference of them. The summation of torques is equal to I times the inertia. So here, that net will be equal to 2 M initial GR initial minus 1.5 M initial GR initial. By the way, this is torque 1 minus torque 2. And this is 0.5 M initial GR initial. So this makes sense because each of the hanging objects, they produce a torque equal to the radius times the weight. And because they're opposing each other, the larger torque is going to win and end up dominating the direction that the pulley system is going to turn in, right? Now, we can think that, or actually, this object is going to be accelerating down. I just realized this is 1.5 M initial. So, object 2 is accelerating down. Now, for our next question, we're asked, object 1 accelerates downward after the pulleys are released. Wait. Okay, never mind. This one goes down. So, that's because we define our axes as this is in the positive direction, and then this one is in the upward direction, I believe. Now, if it goes downward, what we know here is that at time is equal to TC, right? Object 1 is cut, and then the system is still moving. So then we are immediately going to compare the directions of the angular velocity and then angular acceleration. So angular velocity and your angular acceleration of pulley are opposite directions. Now, what is the direction of our angular velocity after we cut it? So after you cut it, you have to remember that object 1 is before the movement. Moving downward, I mean. Therefore, the pulleys are rotating in that same direction. But then post-cut, the pulley keeps rotating in the same direction for an instant. Because your angular velocity, which is omega, doesn't change instantaneously. Now, if we think about the direction of alpha immediately after the cut, you have to remember that object 1 is no longer going to exert torque on the pulley because the string is not touching it anymore. There's no pull happening at a certain R from the center. And object 2's torque is going to be in the opposite direction from object 1's original torque. So the direction of object 2's torque is going to be opposite the current rotation since torque is equal to I times alpha. So alpha is going to be in the same direction as the new torque, and that's how we get that alpha opposes omega, your angular velocity. At a later time t is equal to tc, the string of object 1 is cut while the objects are still moving and the pulley is still rotating. Immediately after the string is cut, how do the different directions of the angular velocity and angular acceleration of the pulley compare to each other? So, from t is equal to 0, to t is equal to tc, they're pulled from rest. So your net torque is going to be a constant. And since your torque net is equal to I alpha, and I is going to be constant, right? Therefore, this is going to be constant too. So if you have constant acceleration, you can use omega is equal to omega initial alpha t. Omega initial equals 0, omega is equal to alpha t. So that means from 0 to our tc, omega is going to be a straight line with positive slope if object 1's direction is positive, direction of motion that is downward, falling down. So then when you're at t is equal to tc, when the string is cut, the pulley angular velocity doesn't jump suddenly. Therefore, our graph is continuous. So there's no discontinuity at TC. After t is equal to tc, object 2 provides torque. At t is equal to tc, the string is cut and the angular velocity of the pulley doesn't jump suddenly. So that means that the graph is going to be continuous and there's no discontinuity at tc because there is no immediate jump, right? So then after t is equal to tc, the object is going to provide, or object 2 is going to provide torque in the opposite direction. So the new alpha is going to be negative if the original angular velocity was in the positive direction, right? So then after we're at tc, your angular velocity is going to decrease linearly with time because of our equation we found over here, right? And that means when we're at tc, that we have a sign change of the slope, right? So then this is going to be our graph. At first it's increasing, then when you get at tc, then it just drops linearly.